Given that an object released from rest near the surface of Pluto would fall about 12 meters in 6 seconds, what is the value of g on Pluto? So one thing that this question addresses is you can use Galileo's free fall formula, d equals 1/2 gt squared, for different planets other than Earth. But the important thing is the value of g would be different. In this case, the question we are asking is, given the information that's there, what is g equal to? Maybe I'll say, I think when I wrote this question, the answer to this was reasonably close to what planetary scientists thought the free fall acceleration on Pluto was. I'm not sure if that value has changed. We haven't been able to go to Pluto and actually just drop an object to figure this out, so it's not as easy as it sounds to get those numbers. And I have seen them kind of change over my lifetime what we think it is. You might wonder, is that something you check regularly? Anyway. But let's see if we can figure this out. So again, g is what we're asking for. We have a d is equal to 12 meters. We have a t is equal to 6 seconds. And hopefully that all makes sense. What I'm basically doing is I've got a formula, I think, that describes this situation. I'm looking at my problem and I'm finding some of the numbers and assigning them to the variables. This is something I sometimes do. If you want to do it and copy me the way I'm doing it, it's great. Make sure you're thinking about, though, how you make the assignments, because sometimes you don't want to just do it like, with your brain turned off or something. But this one's pretty straightforward, I think. And then you can either plug those numbers in and then just solve for the thing you're solving for. What I often like to do, though, is I recognize, hey, this is the one I'm solving for. So if I multiplied by 2 on both sides, I would get this, right? 2d is equal to gt squared. And then maybe I could divide both sides by t squared. And I'm going to write things a little bit differently and say that g, I'm going to, in other words, put the g on this side. G is equal to 2d over t squared. And at that point, I'm going to go ahead and put in the numbers here. And again, exactly what math you want to do for this. Everyone's may do it a little different. Important, don't forget the squared. Sometimes I forget exponents because we're all human. Happens once in a while. And usually if you track units, you'll catch that. That's kind of one of the utilities of looking at units. Even though they won't catch every mistake, they will catch some. And okay, I think, let me see. That's like, what is that? That's like 24 over 36. If you do it without a I was going to go grab my calculator here because I've done it in there, but I think this is actually, and if I check the units here, this is a meter per second squared, which is what I expect. It's supposed to be an acceleration. It turns out, I think 24, right? This is, I think there's some common factor there. I think that's actually, like, I think it's, what is it, like, it's 12, I guess, would be the common factor. So this is really like equal to 2/3 meters per second squared, which maybe as a decimal I could write, I think we're at 2 sig figs here, so I'll go with 0.67. So again, some of you may have heard of, like, some science classes require you to work in decimals. I'd probably be cool with this, but I've often made my slice to sort of fit that sort of ideal. So that's the answer that I'm getting, properly rounded at 2 sig figs, and there it is.